Want to narrow it down for starters to one? Any problems? Which one? Just tell me.
I looked at them all. One of the t to the negative at.
Hold it. Let me get it up here first. We'll do them sequentially. Then I might add, as we're going through this, any property that's needed, I'll explain. All right. Go ahead. Which one is it now?
It was one of the ones you posted. I think it was like
Tell me. What?
t e to the negative at cosine omega t.
Okay. Omega naught t u of t, right?
Yeah.
Has to be u of t. We want the transform of that. Let me tell you how I break this down. Please listen. What I suggest, and you have to know this because I went over this, you have to know that cosine of omega naught t times u of t by itself goes to what? S over s squared plus omega naught squared, right? And you know sine of omega naught t u of t, that goes to omega naught over s squared plus omega naught squared. You've got that. We did in class. Something you have to know. Those are just necessary. All right? Now there's a property that we talked about. Do you remember if you had x of t going to x of s, we assume we know that. Then if I have e to the minus at times x of t, what happens over here is just x of s plus a. How many remember that last time? That's a fundamental property. Now look what we got here. Don't worry about the t. Look here. We have cosine of omega naught t that we know the transform of. Understand? X of t, x of s. Got it, everyone? Therefore, if I multiply that by e to the minus at, everywhere there's an s, I replace it with s plus a. Does everybody understand that? So if I say this is an e to the minus at here, it just means this is going to be, top part is s plus a, right? Bottom part is s plus a squared plus omega naught squared. Understand? I'll get to the t in a second. How many see this? This is the way you expose and use properties. The homework I gave you was just about exposing the properties. It was using them to get the answer in a very obvious logical way. There's no major logical jumps here. It's very apparent what you need to do. Now here, if I do it, I want to do it here. E to the minus at right there. Now what happens? That sine of omega t gave me that, right? That's x of s. Now wherever the s is, I replace it with a plus s. How many see that? And a is any number, right? So this is going to be s plus a squared. Correct, class? How many see that? Now you've got you've got both of those exponentials times sines or cosines that occur all the time. Now what happens if we multiply any x of t by t? Well, if you look at that, I'm going to show you this. This is a property I didn't have time to do, but it's in there. Please listen, I don't want to race through this, but I want to answer this in a way that is most beneficial to you. So if you come across this, you don't panic. Now suppose I want this. I want the transform of t x of t. Assuming I know x of t goes to x of s. So I assume I know that. That's the key. Now, if I look at the definition of x of s, and I'll put it right here, that's equal to the integral from 0 to infinity of x of t times e to the minus st dt. Everybody agree with that? That you must know. You can always default to that if you want to transform. I call it doing brute force and awkwardness. If you really want to transform and you don't see a property that works, just throw it in there. That'll make it work. But the integrals get awkward sometimes. Just telling you. They're not the easiest. That's why properties are used all the time. Now, when I take a look at this, I don't want x of t, I want tx of t, correct? So if I take a derivative of this with respect to s, I take a derivative of this with respect to s. Does everybody see that? What happens? The only thing that has an s in it is e to the st, minus st, right? When I take a derivative of that with respect to s, I bring out a minus t, correct? Does everybody agree? How many see what I'm doing? I'm just doing a simple property, but I'm exposing how the property is created. Now if I have that, I don't want the transform of tx minus tx of t e to the minus st. I want the transform of t x of t e to the minus st, right? So it says if I know the transform of x of t goes to x of s, then if I want the transform of px of t, I take a derivative of x of s with respect to s, and I throw a minus sign in there. How many see that? Now, I asked for the derivative of this, right? Or where this is like my x of t, right? That was like my x of t. And now, what I want is t x of t, right? I want to know what that is. Well, this is my x of s for my x of t. How many see that? So I take a derivative of that with respect to s, and I throw a minus sign. Do y'all see that? And that's my derivative when a t is multiplying. Now the problems I gave you were, I made sure that they kind of made this kind of logical process necessary, and it's very apparent. There should be nothing that confused you about this, because the properties are logically laid out, what I showed you, so you can just deduce the next logical step. I'm showing you how the property is created. So here, I have to put minus, right, the derivative with respect to s, right, of this, which is going to be s plus a over s plus a squared plus omega naught squared. Agreed? That would be what? Minus, take a look at this. When I take a derivative of that with respect to s, I'm going to do the first function, s plus a. That is just 1, right? So then I have 1 over s plus a squared plus omega naught squared. Do you all agree with me here? How many do? Can you see it in the far back, dude? Then I say plus the second, which is plus the first, s plus a. Then it's times the derivative of the second. The second function is 1 over s plus a squared, omega naught squared, right? That's really s plus a squared plus omega naught squared to the minus 1. Do you all agree with me there? Take a derivative of that, I get minus, so I get a minus here. Then I get that quantity s plus a squared plus omega naught squared, right? And then I have to take a derivative of this inside with respect to s, the s plus a squared. Do you all agree with that? So now I get this. I end up getting 2s plus a. Everybody with me? How many see this? And that's the answer. And you can group terms if you want, but that's fundamentally the answer. Do you all see that, class? Give me a show of hands here. Make sure you do. Notice what I did. Very logical, very simple if you go through that. If you've done the homework, you've been keeping up with it, this is just a natural step. There's no big discontinuities. What's the next problem? Y'all see what I'm talking about? You got it, right? This is not that hard if you keep up with it. If you try crayon, you're dead. I mean, you're just failing sideways. Go ahead.
T squared times...
Oh, I thought you had a question about it. Okay. Can I leave that up there? Why not? You got a t squared problem?
T squared times the quantity of u of t minus u of t minus 1.
All right. Now, couple of this straightforward. I'm going to say this. What if I make my function x of t equal to u of t minus u of t minus 1? You give me that? And then I'm going to multiply it first by t, and then by another t. All right? You understand what I'm doing logically on this one, class? Give me a show of hands. It should be apparent to you by now. So first, if I take that as a function, what is x of s of that? We talked about this one, right? U of t function, the transform of that is 1 over s, right? And then if it's time shifted, you get a what? 1 over s times e to the minus s times this 1, right? So now I got 1 over s times the quantity 1 minus e to the minus s. That's the transform of this, correct?
It's a 4, not a 1. My bad.
All right. 4. Agree? I don't care what it is. It's just a constant. Right? Now, go to the next step. What happens if it's t x of t? First time. Class? Got to take a derivative of that with respect to s and throw in the minus sign. Just let me do this, all right? I'm going to just put it up there. So now I go ahead and put minus the derivative with respect to s of the quantity 1 over s times 1 minus e to the minus 4s. Got two functions there, right? Can everybody do that derivative fairly easily? This is one of those things that's an automatic. If you're an engineer, I mean, if you're at this point in your career and you're an engineer, this kind of stuff is automatic. We can do it. We will do it. But you all agree with me so far. Now, what happens if I go this t times this function tx of t? Now what happens over here? Just tell me. Another derivative of this with another minus sign. Does everybody agree? You see the minus signs canceling? Give me a show of hands with that. So now I can really say it's really the second derivative with respect to s squared of 1 over s times the quantity 1 minus e to the minus 4s. And if you want me to do the derivative, I can, but those things are kind of automatic, aren't they? Take one derivative, the result of it, take another derivative. If you want me to do it, I will, but it's just what? It's permutations, it's not hard. How many see this right here? All right, it's very obvious. Now, you could have done, I'm just telling you that you see on quizzes when you grade, you could have said t u of t minus t u of t minus 4 times t. So first you get a ramp function, right? And t u of t, does anybody remember what that one is? 1 over s squared, right? If u of t goes to, right, what? 1 over s, take a derivative of that, you get what? Minus 1 over s squared times the minus sign, 1 over s squared. You follow me? And you can do it all. T squared u of t, you can keep going down that route. And it's not hard at all. Another one. Who asked that? You do. Anybody else got it? You said all of them.
So, question about this: why is it 1 minus e to the negative 4s?
Well,
So I
when
get
you
the
say
negative
u of t
4s.
is 1 over s, you can factor a 1 out of that, can't you? Look, u of t goes to 1 over s, right?
Mhm.
U of t minus 4 goes to 1 over s times e to the minus 4s, right? So why not just factor the 1 out?
Okay.
In that way, it breaks into two nice functions for future derivatives. Understand, everyone? All right, what else? You said all of them. All right. Come on, man. Was that bad?
Is there a property that explains what happens when you do a phase shift of a cosine or sine function?
Yes, we can do those, but you can do them 5 or 6 different ways. In his book, he does it. Let me just show you this. I'm going to do this. This is the way I like doing it. Everybody, y'all remember when you had to memorize all the trig identities? Cosine of a plus b, sine of a plus b, tangent of a plus b times tangent of c plus d and all that crap. And you went nuts with all the permutations that could happen. Here's the easy way to do it. You want a cosine with an angular offset?
Sure.
Sure. So you say, what is cosine of omega naught t plus some phase angle? And I'm going to assume it's times u of t, but I'm going to leave the u of t off for now, all right? What is that? Use Euler's. That's equal to what? E to the j omega naught t plus the phase angle plus e to the minus j omega naught t plus the phase angle, right? Over 2, right? Now listen to me. You all see that? Now, what happens here? And let's assume there's a u of t here. I almost don't want to do this. But now, do the first one. If I have e to the j omega naught t, e to the j theta is a constant. So put it out in front. Right? Over 2 u of t. What does that one go to? Well, the e to the j theta over 2 comes right up in front. Doesn't it, class? Now, what happens to e to the j, first, well, we could do this several ways. Remember, we had e to the at u of t goes to what? 1 over s plus a, right? A here is what? J omega naught, isn't it, class? Y'all see that? So you can just say this is going to be 1 over s plus j omega naught. That's the first part. That one, right? How many see what the second one's going to be? I'll just take that second part. Plus e to the, it's going to be minus j theta e to the j omega naught t over 2. Now what does this one go to over here? How about we just take the constants out in front, e to the minus j theta over 2, right? And what happens here? E to the j omega t plus 2 goes to, actually, yeah, that's right. What happens over there? It goes to, what does e to the 8 minus at u of t go to? 1 over s plus a, right? What if it's e to the plus at u of t? It goes to 1 over s minus a, right? So this one goes to just 1 over s minus j omega naught, right? Now y'all see, you can go ahead and get a common denominator, and then you can go ahead and combine them. That's a perfectly legitimate answer. All right? And that's the easiest way to do it. And I recommend anytime you get like sine squared, cosine squared, and all that crap, they'll have a million different ways to remember these things. I always go to Euler's identity and work from there. Remember that. It'll save your life. Because in some of the craziest stuff I've run into, I'm not going to go and look through the tables about a tangent cube, cosine squared kind of formulation for an integration. I turn them all into exponentials, and it becomes very apparent. Next one. What else you got for me? Anybody else? What? You're kidding. In a way, I'm pleased. In a way, I'm not. I showed you some tricks. I got to go through a couple other things, properties with you, okay? Now, well, if I'm really honest with you, there's a host of things we could get that are not the obvious properties and put down, but they're not really useful. So, I'm going to show you ones that I think are really useful, and I use them, and you will too. And I use them in the work that I do at times day to day. So it's not something that's, just here and abstract, you forget about. This is stuff you're going to use. One of the things I talked about, are two things when you have derivatives. If I have x of t goes to x of s, then the logical thing is what happens if I have a derivative of x of t, right, with respect to t over here. For this one, we'll look at the actual Laplace transform definition. And if I say that I have x of s is equal to the integral from 0 to infinity of x of t e to the minus st dt, that's fundamental, right? Now, if I take a look at that, and I want to know what the derivative of x of t would be. So now, in his book, I think he shows this proof, but I'm not sure. I'm trying to think of the easiest way to show you this. This is u, this is dv. Now, you remember when you do integration by parts, right? For integration by parts, it's u times v. So if I said I had dv, is equal to e to the minus st, then du would be equal to, and it's with respect to t, is going to be minus s times e to the minus st. And if I say dv here is equal to the x dt times dt, then I can say v itself would be x of t. This is just the usual partial, it's the way you do integration by parts. Do y'all remember that? How many do? And if you're wondering how to get that, I have people ask me this occasionally. Whenever you're thinking about integration by parts, think of two functions, and you want a partial derivative of that, all right? So for that, regardless of what your derivative with respect to x, t, it doesn't matter. This is really going to be the first, or derivative of the first function, du, forget the dx, times v, plus the derivative of the second function, dv times u. So if you therefore wanted the actual value of that, dvu, you would say the partial with respect to uv, the product of the two things, minus the partial with respect to u times v. And then you would integrate both sides. Do you understand that, class? That's the simple way to remember this. How many understand what I'm doing right here? Now, in my case, I know that if I got dx dt, that is a differential. It's a no-brainer here if you've worked these for a while. You know that's going to be the differential, understand? Whatever remains, the e to the minus st is going to be the u. So what is this equal? Well, that's equal to u times v, or it's x of t, right here, x of t times e to the minus st. And And that integral's from 0 to infinity, and it's minus, then it's going to be, it's going to be du, that's u times v, and then it's going to be minus s e to the minus st right here, and it's going to be from 0 to infinity. Now, when you evaluate this, this is as t goes to this. This is t goes to this. For this first one, for this one right here, as t is 0 right here, or sorry, when t goes to infinity, this term goes to 0. Do you agree with me, class? And here, as t goes to 0, it's minus. You can see this is going to be e to the 0. E to the minus s times 0 is simply e to the 0 is 1. Do you agree with me? So this part becomes just minus x of, and this would be t equals 0. Now on this side, when I go to infinity here, it goes to 0. Do you agree with that? Because it's e to the minus st. When t goes to infinity, e to the s minus infinity goes to 0. Do you agree? Then the last part here, when t goes to 0, right here, I have minus s, right? And then it's going to be, oops, sorry. And really, that would be x of s here. And he does this in the book, so I'm just going to put this here. This particular property is going to be s times x of, actually that's a plus, pardon me, x of s minus x of t equals 0. This one should be in your book. Does anybody see that property shown, how they do it in the book?
It's on the table of properties.
Not tables, but this, he actually derived this. It's integration by parts is the way you get this. He should show you that one.
Yeah, it looks like there is one for the first and second derivatives.
He should have this form, s x of s minus x of t equals 0. Does he have that one?
Yes.
All right, now, if you take another derivative of this, second derivative of x of t with respect to t squared, here's how you do this. You can call this a fictitious function. Call this x1 of t. Now I'm really taking the first derivative of this one. Am I not, class? So then you would simply take, since this is now, I mean, this dx dt goes to that. Now if I want the second derivative, I go ahead and I say it's simply going to be this with x of s. This whole thing is x of s and it's times that, but I'll just tell you what it becomes. It's going to be s squared x of s, and it's going to be minus x, s times x of 0. That's the value of x of t evaluated 0, minus, and then it's going to be s squared, or excuse me, it's minus, I got that wrong, it's minus, yeah, s times x0, and then it's going to be minus dx dt at t equals 0 as well. Do you understand that, class? Is that in the book too, this form?
Yes.
Now these are really valuable. The one you always remember is this, because from there you can get all the others, no matter how many derivatives you use. All right? I'm wondering about this proof in the book. I don't know if he showed that. Anyway, that's for another time.
It looks like it did integration of parts the same way you did it.
All right, I'm just thinking, well, I'll tell, I don't want to waste time on that right now, but I didn't look at the way he did it in this book. Now the next property, if we do integration, you should also ask yourself the most likely next question is, what happened if I have x of t goes to x of s? What's the integral of x of t right here, dt, and this would prime it, and go from, say, 0 to t. Now, in this case, we've got a function that we're integrating, right? The t prime's there because this is a dummy variable. When you do the integration, it naturally drops out, and now you evaluate the limits from 0 to t. Understand? So if you do this one, in the book, he has this also, I believe. He'll show it as a property. And this one is going to be what? It's just 1 over s, x of s, if you look in your book. Do you see that? Here's the way you remember it. Derivatives bring out s. In front of them, integrations are 1 over s. Follow me, class? I'm not going to prove that one. Oh, it's only 28 up here. Okay, I thought it was later than that. Everybody with me? Those are 2 properties that you can use. I can prove that one right now, but I don't think it's necessary. It should be proved in the book. Other questions? Those 2 properties are really important. I told you about convolution in time of 2 functions, multiplication in the S domain, right? Now, the other properties that he has listed in the book, I'll just tell you this is my opinion. Linearity is obvious. Constant multiplication. Time scaling we did time shift. We did frequency shift effectively. We did first and second derivatives. We did integration. We did Tx of t. Well, we can do x of t over t too. I don't think I'm going to have time to prove this one, but if you had x of t, you know x of t goes to x of s, then if you had x of t over t here, well, remember when we had tx of t, you remember what happened? You had minus derivative with respect to s of x of s. Do y'all remember that class? Well, if you have this, if you have a 1 over t, that effectively is going to be integration. I can prove this if you want me to. But this goes from s to infinity here of simply x of s times ds. And I got to prime these s prime in there. Isn't that what he has in his book for this one? And this is just things, if you work with them, you know. You can prove this fairly easy by the fundamental definition. Remember when I did the one where I want tx of t, I took a derivative of x of s with respect to s, right? Here you take an integration of x of s and you get that. If you do the integration of x of s, you get the 1 over t out front. Understand, class? But the limits have to go from s to infinity. And as far as the other properties go, I'll tell you about the initial. Well, today I won't mention initial and final value. I'm going to tell you that those are really not that useful, to be frank about it. I'm being honest with you. In my years of engineering, I think I might have used one of these a couple times just to verify answers, but they're not used that much. All the ones I'm showing you, I use these routinely. I have to apply them for things, but I do radar work. If you do communication work, anything where it's things where you're talking about a lot of data throughput, you're going to be using these kind of things, controlling the system and stuff like this. So please be aware, this is not something abstract. You're going to be using it unless you're in sales. I'm going to tell you the truth. I ran into this is a short story, but it's a true story. There was one person who I had very little confidence in their ability to walk a dog. The person had an engineering degree. This is an overstatement, but you get the idea. And the person did have a personality. And sure enough, that person ended up in sales, doing a great job, because a talker that knows very little about the actual technical stuff is just who you want out there, because they don't know anything about it either. They just want to hear you talk and tell them it's great. Enough on that. Just like a car salesman. They're not mechanical engineers, right? Think about that. Now, the next thing I want to do is tell you, you'll use this stuff with you. Gosh, I don't know what about that. See by Ford Motor Company. So now I want to talk to you about, now that we've established the basic understanding of how to get the Laplace transform, the next thing you have to ask yourself is, well, once you got the Laplace transform, how do you get the inverse Laplace transform, or the time domain form that's observable? So, and I'm going to tell you one other thing before I go that route. I'm just going to say, why are Laplace transforms so interesting? All systems that we have are described in terms of one of 3 things. Well, one of basically either differential equations. Remember that, if it's continuous time. If it's not continuous time, it's difference equations. Or block diagrams, input with h of t, the impulse function, or the impulse response, being convolved with the input to get the output. That's convolution, block diagram. Those are the 2 ways all systems are described. And because of that, Laplace transforms can be used. If it's convolution, you take the Laplace transform of the first and second function, h of t and x of s, x of t and h of t, you get h of s and x of s. Multiply them together, you have y of s. But you don't have the time domain form. Then you have to do the inverse Laplace of that. If it's differential equations, you know the second derivative of y with respect to t brings an s squared y of s minus s, y of 0 minus derivative of y with respect to t evaluated at 0, right? If it's a first derivative, it's just s times y of s minus really y of 0. But you can easily construct the Laplace transform of a differential equation and solve it. And then, once you solve it in the S domain, you can do the inverse Laplace to get the time domain form. Now I'm going to show you how we do inverse Laplace transforms. And I'm going to tell you this. In general, there's about 4 different things that happen. We start with something everybody knows. When we had this e to the minus at times u of t, that went to simply 1 over s plus a. Correct, class? We know that. Right? Now, if we know that, then I can say that if I have a function, I have some h of s, and it equals to, say, 10 over s plus a. Or matter of fact, I'm going to put hard numbers here. S plus 5 times s plus 10. And I want to go ahead and find out what the h of t is for this. If I know this relationship, and this is one you have to know, I can do it by using partial fractions. And by saying partial fractions, these are called simple poles. It's s to the first power, and it's added to only one other term. It's s plus a. So I can break this down as some a over s plus 5 plus b over s plus 10. You all agree with that? Now, how many remember partial fractions? They were a godsend. Some of you don't remember. Well, this is the only way you can do Laplace transform, the inverse is this way. I mean, if you want to know the truth, just to be, if you ever had a professor do this to you, I'd so. If you ever had somebody say that x of t was equal to 1 over 2 pi j, this is actually correct. The integral from minus infinity to infinity of x of s times e to the st dt, this way ds, that is correct. It is also a nightmare usually to do that. So we don't do that. We can do that if we're so inclined to be nuts, but we don't usually do it. We do it with partial fractions where we know, yes sir?
I'm not necessarily sure this is faster, but could you also use the convolution property to break it up into e to the negative at functions?
You're going to say that it's this times this would be x of t convolved with, yeah, but then what are you going to do? You still got to convolve it.
I mean, that's what I'm saying.
You don't want to convolve it.
Faster, but
No.
wouldn't it work at least?
Convolution bad. Keep saying that. Now you come here and you say, if you want a, the way I talk about is the cover-up method. I'm not going to go through, you've had this really, I know you have. The easy way to get a is you multiply both sides by s plus 5. That's the pole. This is called the pole when s equals minus 5 actually is the pole. Follow me, class? That makes this term, s plus 5, go to infinity. And when I use the term pole, I'm assuming you're familiar with it, but if you're not, when you talk about what the poles of a function are, they're the values of s that make the functional form go to an infinite value. Here, if you take a look at this, when s is minus 5, it goes to infinity. You all agree with that? That's a pole. Over here, s would go to minus 10. That's infinity. Those are the poles. Got it, class? So now, if I want to get this, a, I multiply both sides with s plus 5. So that cancels that, and I get s plus 5 here. S plus 5 over here gets rid of s plus 5. Then you evaluate the remainder when s is equal to minus 5. You'll notice here I have 10 over minus 5 plus 10, which is equal to what? 10 over 5, which is 2. Do you agree with that, class? Over here, I just have a because the s plus 5 canceled, right? Over here, I have s plus 5. S at minus 5, I have 0 times this, so that goes away. So therefore, I have a equals, you just cover up. This is called the cover-up method, you probably remember. For a, to get a, I simply cover up the pole that a's evaluated at and evaluate the remainder at the pole, which is s is minus 5, which is 2. Does everybody see this, class? You've had, how many remember this now? You all have had this, it's very easy. How do you get b? By inspection, what is b? Cover up what? S plus 10, correct? Then take a look at the remainder evaluated at S equals minus 10. What is the value? Minus 2. Agreed? And that's typical whenever you have two poles and a constant there. They'll always be opposite signs, same magnitude. So here, I'm going to have this go to 2. I'm doing this one in its entirety. And this go to what? Minus 2. Correct, class? Right? Now go back to the time domain. What does this one go back as? Just by inspection. Knowing this. Class, what? 2 times what? 5t times u of t, right? Minus 2 times e to the minus 10t u of t. Follow me? That's simple partial fractions. Now, the next thing I'm going to say is if you have, actually, I probably don't have time for this, but the next thing I'm going to do is not if you have a simple pole, but if you have what's called a double pole, if this is squared. I'll get to that next time. I'm about out of time on this one. I am glad you asked some questions. I had time to go through some of these things. So do me a favor, spread out as much as possible. Try to get at least an empty seat between you and your neighbor. You and your neighbor, take everything off your desk. You can have nothing you're sitting on, so I'm going to ask you to stand up, take your phone, and turn it over and put it on the desk. You cannot use any electronics, no electronic watches, no calculators, nothing. No phones.